who actually I first met via email before I actually even arrived on campus. Grant asked to work in my research lab, and he helped me set up my research lab. He's been with me for actually just the first year. You decided PChem was for you, and then you quickly discovered that organic is probably much, much better. Not because PChem was hard, but because organic was harder. And the idea, well, I'm getting to it. And the idea that there were complex questions that take life to answer. And Grant is one of those fantastic people who likes to answer all sorts of different questions. Answer questions in the conservatory, can you play your bass in this way? Answer questions philosophically with the philosophy department. Answer questions both between me and Stefan, which is kind of fun. So he's really suspended in all these different types of languages, which is great because the first thing about being a P chemist is make friends with an organic chemist because you don't know how to make molecules, they do. So Grant actually made some molecules for me later on. He's been a translator between me and Stefan, which is fantastic because we definitely don't speak the same language. However, Grant decided for senior experience to return to the wonderful world of PChem, which is really a fundamental language of how we understand fluids. So I'm very excited to hear what Grant has to say about the self-consistent picture of fluidity and the application of the compensated Arrhenius formalism, sorry, I get excited, to 1 and 3 alcohol systems.
Well, thanks for coming, everybody. Yeah, I'm going to present to you a self-consistent picture of fluidity through this formalism and its application. So, first thing I'd like you to do is just watch this video. Right? So, on the top, we see what is called a very fluid liquid. It moves quite well. On the bottom, maybe I'll play it again. The cube drops in and nothing really happens. This is what we call a very viscous liquid. So first thing I want to get out of the way is that viscosity is the inverse property of fluidity. Okay, so what I want to know is how the molecules are moving in these two liquids. Now it looks like they're moving quite differently. They're behaving very differently. But what's going on at a fundamental level? Are there certain nuanced differences between these systems that we can tease out and figure out what's really the difference? Is it how they're moving or is it the structure of the liquid? And what I'm going to eventually say is that the way the molecules move, the mechanism that they move through, is the same in both cases. However, there are certain differences that arise from the structures of the liquids that cause them to behave differently. So, sort of the reason we're doing this is that we want to build up a self-consistent model. We want to get to a picture of fluidity that works for these two different systems, and we want to be able to describe them ultimately in the same way. So that's what we do in the Fleshman Lab. We look at these different systems, a lot of different systems, and apply this model and see if it fits the data. So the model then is a model of thermal activation. So what that means for us is that this molecular motion is an activated process. It takes a certain amount of activation energy to get the process to go. So if you look at this diagram at the bottom, you see on the y-axis we have energy increasing. We start at an initial state where there's sort of a cage around our target molecule that we're looking at, the one in red. Right? And so the activation energy is supplied to the system. The cage opens up. The other molecules orient, and then the central molecule is allowed to move out of that, into that hole. And then, of course, we move back to the final state, or we move to the final state, I suppose, but it's at the same energy as the initial state. And that's from the relaxation of the oriented molecules. Some things about the activation energy. The activation energy is temperature dependent. So when it comes to a sort of temperature-dependent description of fluidity, it's not going to be necessarily the key. But the liquid structure is temperature-dependent, so that's something we want to keep in mind. And what sort of systems am I interested in? I said before 1 and 3 alcohols, but what are those? Here is a 1 alcohol and a 3 alcohol, excuse me. They're both octanols, which means that they have 8 carbons in their chain, which is represented by each of the points, and then bonds are the lines between them. What makes them an alcohol is what's called the functional group at the end, or on the 3rd position here. That's called a hydroxyl group, or an alcohol group. It's an oxygen and a hydrogen bound together. And these functional groups have interesting effects. They do interesting things. they fall in a class called polar protic molecules, which means that they hydrogen bond, which I'll get into later. So these sorts of molecules are representative of a large class of molecules. They're well understood molecules. We have lots of data about them that we can get from the literature, which is pretty easy to find. They're simple molecules. They're not incredibly complex, so it helps us develop a very, very fundamental picture of what we're doing. But it could be the basis for understanding much more complex systems. So say we put an alcohol onto a slightly more complex molecule, maybe we can learn some things about it if we know how these sorts of molecules move fundamentally. As I mentioned before, we can vary the shape of the molecule by changing that hydroxyl location. So here it's on the 1 carbon, here it's on the 3 carbon. And finally, by so doing, we change the hydrogen bonding characteristics. So I've talked about hydrogen bonding a bit now. So hydrogen bonding is a strong dipole-dipole interaction. Over here, we have a partial negative charge situated on the oxygen of this water molecule, and then a partial positive charge situated on the hydrogen atom of this water molecule here. So this is what's known as the hydrogen bond acceptor, and this is what's known as the hydrogen bond donor. Okay? So this interaction, on the scale of just 2 molecules binding together, is not particularly strong. However, en masse, in a liquid, the likes of which I'm studying, it's going to probably cause some significant effects and ultimately determine some things about the structure of the liquid. So now comes the question, how do molecules move? Well, here's a plot. We have fluidity increasing on the y-axis, so things are becoming more fluid. They're pouring easier up here than they are down here. And we have temperature heating up as we go along the x-axis. And as sort of a wide scope representation of the systems I'm using, the shortest chains we ever used were 6 carbons long, these hexanols, and the longest we used were 10 carbons, these decanols. So this is sort of the outer limits of the work, the molecules that I worked on. So at high temperature, we can make a fairly convincing hydrogen bonding argument as to why they're behaving in this order. Sort of the star is the 3-hexanol. That's not really hydrogen bonding as much as the 1-hexanol is. So we would expect it to move a bit better. As well, these are much larger, and for similar reasons, the 3-alcohol is going to be more fluid than the 1-alcohol. But when we lower the temperature, we see sort of different characteristics starting to emerge. Particularly once we get around 25 degrees Celsius, we start to see an overlap between the star and the little black box, the 3-hexanol and the 1-hexanol. So this is not described by that argument that I just gave. So from that, we wonder, how can we sort of account for this in our model? How can we improve on the arguments given? So the transition state theory that we're working with is described typically by this Arrhenius type equation. So we have our fluidity, F, is equal to a prefactor term, which we're going to say is temperature dependent, multiplied by Boltzmann's factor, which is the activation, or an exponential with the negative activation energy divided by the gas constant times the temperature we're looking at. So what we need to do then, we have this bit, we have the temperature, we know what the gas constant is, we have to figure out what that F naught term is, the prefactor term is, and we have to figure out what the activation energy is. So first we have to get our fluidity values proper. We need to do that with some amount of control. So this is the glove box that I worked in. It's a nitrogen atmosphere glove box, so the atmosphere is inert. Most importantly, it's not really that easy to get things in and out of the glove box if you follow the procedures, so nobody's going to really be messing with my liquids, and I want them to stay pure. Not that anybody would do that, but you never know. So this affords a high degree of control, we'll say. We maintain temperature using this thing here. This is called a Huber mini-stat. it essentially is just, there's a coil in here and it pumps liquid into the glove box to the viscometer, which you can see right here. It's that white box behind the glove. There's it up a bit more closely. This is a Cambridge Viscosity Fisco Lab 4000 falling piston viscometer. So what you do is you put your liquid sample into this little hole, and then you put in a piston, which is ultimately what's going to help you measure viscosity. You start warming up your system to whatever temperature you want. We did temperatures from 5 degrees Celsius to 85 degrees Celsius in 10-degree increments. We would let that equilibrate once we got to the temperature for about 15 minutes or so, and then we would take a measurement. And essentially taking a measurement is me pressing a button on this box, which tells some electromagnets to fire, which moves the piston up and down. And the time it takes the piston to move through the liquid will tell the viscometer what viscosity we're looking at. So we get the viscosity, and then we can very simply translate that to fluidity. Now back to it. So we get our data for these alcohols, and we do our scaling procedure, which I can go into more later, but I don't want it to be the focus right now. And we get activation energies of 36 kilojoules per mole for 1 alcohols, and an activation energy of 34 kilojoules per mole for 3 alcohols. So first thing to notice is that these things are very similar. Things that don't fit into this polar aprotic category are very different. They have activation energies about 10 kilojoules per mole lower than this. So we need something more than the activation energy to understand these transport events. We need another point of view. So if you see, I've added this extra term, this epsilon sub s, which is the static dielectric constant, which is a temperature-dependent quantity, and that's going to tell us something about the temperature dependence of the liquid. Now, why am I using that? Well, like I said, it's a temperature-dependent property, so that is something that has the right sort of functional dependence that we're looking for. This dielectric constant is a measure of the ability for these dipoles to orient in an electric field. So how easily it is for them to move from this sort of conformation to this sort of conformation. So by extension, that's a measure of our structure. If you look at these plots over here, this is the static dielectric constant increasing on the y-axis for 1 alcohols on the top and then 3 alcohols on the bottom, and then temperature is on our x-axis. If we look at the top plot of the 1 alcohols, they all follow a very similar trend. And they're offset a bit, but they're all very linear, and more importantly, they have very similar slopes. So they're changing over temperature very similarly. The functional dependence of the static dielectric constant on temperature in 1 alcohols is pretty much the same throughout the range. Now, 3 alcohols, we have something very different going on. First of all, you notice the behavior isn't nearly as linear. But when we get a slope from the trend, we also notice that they're not even close to parallel. They're going to converge pretty quickly, it seems. So the functional dependence on temperature of the static dielectric constant here is going to be different within the family. So the 1 alcohols are sort of changing similarly, but the 3 alcohols are all changing differently. So this is the same plot. I've just sort of condensed it down, only showing the data that I've been showing with the fluidity. So again, static dielectric constant and temperature. So 1 alcohols here in the black and the green, and then in the sort of teal stars, we've got 3-hexanol, and then these blue hexagons are 3-decanol. Sort of comparing them up close, we see that 1-hexanol changes pretty decently. 3-hexanol also changes pretty decently, and so does 1-decanol, but 3-decanol, on the other hand, hardly changes at all with temperature. So we need to be able to account for this. Now we can sort of start to ask, why are they behaving differently? They have the same activation energies, they have the same intermolecular force, hydrogen bonding, they have analogous chain lengths between the 2 systems, the 1 alcohols and the 3 alcohol family. The difference is just how they're behaving, but they move the same. So what's the difference? On our model, fluidity is described by this sort of transition state, which is brought out by this equation mathematically. Pardon me. Serious. Well, I won't give it to them. So we have roughly the same value of the Boltzmann factor in really any system we pick. Any alcohol we pick, that part's going to be pretty much the same at any given temperature. This part then must be the part that's changing. Incidentally, hydrogen bonding is going to change or going to affect the static dielectric constant, and that's going to change the fluid character. So this hydrogen bonding is something we have to examine now, but how do we do that? So here's sort of what hydrogen bonding among alcohols would look like. We've got this donor going to this acceptor, this in turn being a donor, and this only being an acceptor. So there are sort of different conformations of hydrogen bonding that we can have, but most importantly, we're measuring the energy of this bond, the OH bond that I've highlighted in red. And how we do that, we take our sample, stick it in here, and we have this light source in our interferometer downstairs. We shoot a light at a wavelength selector. In our case, it's a mirror, so it doesn't quite work exactly like a wavelength selector, but that's not really important. The light goes through the sample, and then after the light has gone through the sample, it hits the detector, creating electrical impulses that go to a computer that spits out a spectrum. So we're going to focus on a part of the spectrum that's only concerned with the energies that these bonds take, those in red. And if we see shifts that shift to a lower frequency when we manipulate the system, we're expecting to see an increase of hydrogen bonding. Why do we expect to see that when we shift to a lower frequency? Well, a lower frequency means that there's a lower energy of vibration. So if all of these things are interacting and hydrogen bonding together, we would expect to see some sort of dampening effect on the vibrations. So they're going to be at a lower energy. If we see a shift to a higher frequency, a higher energy, we would expect to see less hydrogen bonding, right? So if one molecule is allowed to sort of be free from this extended structure, the oxygen and hydrogen can easily vibrate without anything hindering that vibration. So getting down to it, the one alcohol spectrum, we've got hexanol on top in the dark line here and here, and then the dotted line is decanol. These spectra were taken at 15 degrees Celsius and 71 degrees Celsius. So, initially, at the lower temperature, we see very similar hydrogen bonding characteristics. They're almost right on top of each other. They differ in one wave number, which is hardly anything. And then when we heat them up and take the spectrum again, we see that the shift is almost identical between hexanol and decanol. Again, with only one wave number difference, but it's close to negligible. So, what we conclude, same shift, same hydrogen bonding characteristic, same sort of temperature dependence of hydrogen bonding. 3-alcohol acts a bit differently. So 3-hexanol on top, and then 3-decanol on bottom, and then 15 degrees Celsius. This one's at 67, this one's at 75, but it's just higher and lower temperature is what's important. So initially, we see pretty different characteristics at low temperature. Decanol, right around 3363 wave number, is already experiencing less hydrogen bonding than is the hexanol. When we heat them up, we see pretty different shifts. The bottom spectrum, the decanol, hardly shifts a bit, and then the hexanol shifts quite a bit. So we see these different shifts. There must be sort of differences in the way the hydrogen bonding behaves and differences in the temperature dependence of the hydrogen bond, and that is the key. So to sum up, hydroxyl group location alters the temperature dependence of hydrogen bonding. 1-alcohols, they have a much more complete extended structure. The way that they hydrogen bond is very similar, so they're going to experience a similar temperature dependence. which is why when we saw the static dielectric constant plots, they had pretty similar slopes. So that's a pretty good indication that we can use the static dielectric constant value as a sort of measurement of a structure, and we can confirm it with hydrogen bonding. In 3 alcohols, we would expect to see something different, right? Because they hydrogen bonded differently. The 3 alcohol hydrogen bonding is hindered, so the extent of the hydrogen bonding is less than that of 1 alcohols, and the temperature dependence is different, excuse me. And that should be borne out in the way that the static dielectric constant changes with temperature. As you remember, 3-decanol hardly shifted at all. The static dielectric constant has hardly changed at all over the temperature range. Similarly, 3-hexanol shifted pretty well, so we would expect it to shift. And we would expect the static dielectric constant to change over temperature. All right. So now that we've sort of got everything together, we can ask the question, did I help make this model self-consistent in any way? When we start with our fluidity data, we ask ourselves the question, why are they behaving this way up here, but differently down here? Why is it that 3-hexanol and 1-hexanol are crossing over? Why are they sort of changing characteristics at these low temperature ranges? When we think about our model, and we think, well, it must be structurally dependent. There must be some sort of structural element to this, because we know that activation energies are temperature independent. Putting it into our Arrhenius type equation, we know this part has the similar activation energies due to that functional group dependence. So that's our sort of means of explaining the activation energies being similar. That part doesn't change between the alcohols for that reason. But any differences in fluidity then must be described by this this prefactor. Any differing behavior due to hydrogen bonding is going to show up in the static dielectric constant value, which is also temperature dependent, thus altering the prefactor. So when we plot the static dielectric constant against fluidity, we should see a nice master curve formed, but they should be different for the 1 alcohols and the 3 alcohols because they behave differently and have different functional dependencies in this prefactor. Otherwise, we have a problem, but we don't have a problem. So here are the 1 alcohols, and you see they follow along this nice master curve. There are a bunch of different colors and shapes in this plot, but what this actually means is that whatever data point in the temperature range, with whatever alcohol in the 1 alcohol family, they're all following that same trend. They're all following this functional dependence. 3 alcohols, on the other hand, are behaving differently. They follow a different functional form than the 1 alcohols do. This is what we would expect. So really what these 2 plots are showing is that difference between the functional dependence in 1 alcohols and 3 alcohols over this temperature range. So to conclude, if we assume a thermally activated process like we do in our lab, we can do a couple of things. We can isolate the different contributions of intermolecular forces to fluidity. That means that we can ascribe activation energies to shared functional groups, and differences in fluidity to this prefactor term, which is due to differences in the liquid structure. And 2, the temperature-dependent fluidity that I'm trying to describe can be described across this broad temperature range using the same models with systems that behave differently. And we can account for that difference, and it shows up in our master curves. So, future work. All of this is currently in a paper that's in revisions right now that Professor Fleshman and I are working on. Mostly Professor Fleshman at this point because I'm on the outs. We want to apply our model to highly viscous ionic liquids. Ionic liquids are sort of small organic molecules that have a charge, so they're ions, but they behave as liquids, or they are liquids rather, at room temperatures. That's being worked out by the people working in Allison's lab now, and the current data are showing similar fluidity trends, or the trends that we would expect to see relative to our model. So that's mainly what Gus Lowry is working on, is elucidating the similarities. Ionic liquids with hydrogen bonding are going to be worked on with Wes Petcher's continued study. Then high viscosity liquids are being studied by Ben Clark, or were being studied by Ben Clark, he's senior too, he's also on the outs. My future work is at the University of Iowa, where I will be doing organic synthesis, so something very different from this work. I'd like to thank Lawrence University, the Department of Chemistry at Lawrence University, the University of Oklahoma Department of Chemistry, Dan Martin for helping me get all the alcohols that I needed, Tyler Herman and Carmen Sullivan for being the best lab mates ever, Dave Hall and Chem 680 for helping me forcing me to make this presentation, and Allison Flesh, my research advisor, for letting me work in her lab. Thank you. Are there any questions?
So was there a specific reason that you picked 67 degrees for the one instead of 75? Like something happened?
So those spectra were taken at University of Oklahoma when Professor Fleshman was doing her doctoral work there.
I can answer the question.
Yeah, sure.
There was a tornado and it hit the power, and the power supply that we had, the previous one, it worked, and then I was doing the 3 alcohols, and then there was different power supplies. So I made friends with someone in the physics department, got a different power supply, and that's as high as I could go.
Oh, okay.
That was my fault.
Tornado.
Tornado.
Is there a practical application to your research?
Well, sure. So if we understand fundamentally what's going on in terms of liquid motion, we can totally apply this to what's going on in industrial applications in terms of flow chemistry and stuff like that.
Cool. Thank you. Sorry if that sounded snotty.
No.
Follow-up question. So you study fluidity. Are there other transport properties that this formalism can be applied to?
Yes, Professor, there are. We can also apply this to diffusion and the conductivity of. Is there another?
Dielectric relaxation.
Dielectric relaxation.
And rate kinetics or reactions.
All those things.
And molar conductivity.
Professor?
So I don't know if you'll be able to answer this question, but when you have your, can you back to your IR picture?
Sure. Either one in particular.
Just in general.
Sure.
So I'm just curious, you've shown a very small section of the IR, and I would be curious to know how, you're saying this one doesn't matter, but then a slightly bigger matters, and how do you know that those are lined up within one? What's the error that you're associated in, basically that from IR to IR your scale is the same? Do you have a place you're normalizing that? Do you have a place you're checking that that worked out? And then what makes a significant shift and what makes a not significant shift?
So these were all taken on pencil, right? Okay, so these were all taken on the same instrument. It's a Brooker IFS 66B Fourier transform interferometer. So it's got an error associated with it of about half of a wave number. So they are different shifts, but on average, the population size being so large, really it is qualitative. I'm not saying that this is a quantitative measurement. I haven't done that work yet, or I'm not going to. But to answer your question, I guess what is a significant shift is, are they or are they not moving similarly relative to each other? In this case, I think it's fairly clear that they are. They've shifted 30 wave number. I guess I would call that significant, but I might not call the 3363 to 3375 significant, so that's what, 12? Yeah.
And if you blow this up, there's nothing that should be occurring at the same place that you could check to see if that had a shift?
No, I don't believe so.
So maybe Professor Fleshman can answer this one if you don't know. Sorry. Just a point of question. So dead. Okay. I'm talking about IR. So your IR peaks go up. Mine go down. Why is this?
Because chemists like it better that way.
Organic chemistry.
Yeah, I'm conflicted.
Yeah, I don't know.
Upstairs, downstairs war.
Pretty.
So this is an absorption.
Oh, great, okay.
It makes, where do the bumps move to versus where do the valleys? Valleys just seem so negative.
Yeah.
It's transparency, man. Who can get through it?
Now yours normally,
So you know.